All right, this is our review for the modern physics exam. So you've had this and you have a paper copy. I'm just going through and kind of talking about what we're going to have. So the table below has measurements for the maximum kinetic energy of photoelectrons emitted from a metallic surface with different frequencies of light. So we're going to shine light on a metallic surface and we're going to tune the frequency. And so each frequency of light here is times 10 to the 14th hertz, 5, 6, 7, 8, 9, times 10 to the 14th hertz. We need to remember that. As we increase the frequency, we see that the energy of the electrons ejected is also increasing. Now, we're going to draw the graph that is the estimate, and we're going to draw the best fit line on our graph. So the first thing we need to do is graph stuff. So the first one is 5 and 0.1. There's my first point. The second one is 6 and 0.45, so that's halfway in between those two. The next one is 7 and 0.95. The next one is 8 and 1.3. The last one is 9 and 1.45. So it kind of looks like that. Now it doesn't look like an exactly straight line, but it is good enough. So we'll draw our best fit line on here. Our best fit line looks something like that. So that's part A, we're done. Find the threshold frequency for this material and the value of Planck's constant in terms of electron volt seconds. Briefly explain how you did this. So everybody's is going to be slightly different. For the threshold frequency, we know that that threshold frequency is the first time we see it moving. It's going to be the x-intercept. And so looking at that, we can say that, oh, mine looks like it's about 4.8, but you could have a range in there. It's going to be between 4 and 5, but 4.8 times 10 to the 15th hertz. You have to include that last little bit of the unit. And then the value of Planck's constant, well, for this, because it's maximum kinetic energy and frequency, that maximum kinetic frequency is HF plus, apologize, I always do that, minus our work function. So that makes H the slope of our line. So if I want to figure out what Planck's constant is in terms of electron volt seconds, all I need is the slope of my line. So we're going to find the slope, and the slope in this case is equal to Planck's constant. To find the slope, we need 2 points. So our 2 points, I'm going to take this one up here. I'm going to take that one down here. So we have, according to my graph, the y is, sorry, that's y1. y2 is 1.5 electron volts minus y1, which is 0.1 electron volts, divided by 9 times 10 to the 15th. Sorry, that's 10 to the 14th. 9 times 10 to the 14th hertz minus 5 times 10 to the 14th hertz. Now, since we said h was equal to the slope, that's going to give us a direct calculation of h. And so what we'll do is put that right into the calculator here. I'm going to turn that bad boy on. So we're going to do parentheses 1.5 minus 0.1 divided by parentheses 9. We're going to use the e times 10 to the 14th minus 5 times 10 to the 14th, giving me a value of 3.5 times 10 to the negative 15th. So what I get here is 3.5 times 10 to the negative 15th electron volts times seconds. That's Planck's constant. Now, when we pick our numbers, and this is just a note kind of outside of what we need to know for photoelectric effect, these points come from intersections, not data. That's a very important thing. So this is an intersection where my line crosses a grid point, and this is an intersection where my line crosses a grid point. That's how I choose it. In general, we're not going to use data points. This one happens to line up, and it's okay, but this was not a data point. So we're not going to use data points. We're going to use things from our best fit line. Describe how you could adjust the experiment to vary the number of electrons. All right, so in the photoelectric effect, the number of photons determines so more photons gives us more photoelectrons. So whatever we do, we need to get more photons. In order to make that happen, we're going to increase the brightness of the light. That gives us more photons. In the photoelectric effect, brightness tells me number of photons. Frequency tells me not number of anything, but frequency tells me energy of the photon, which is related to the kinetic energy of the ejected electron. So, moving on to our next one. Number 2, we have a hypothetical sample of gas. They're initially in the ground state, and we know that that ground state is negative 5.6 electron volts. White light is passed through this sample, and we notice that we have this light absorbed by the gas. Determine the energy of photons in these wavelengths. Okay, I know that energy is Planck's constant times the frequency. I could also say that it's Planck's constant times the speed of light divided by the wavelength. So for each of these, 525 nanometers, the energy associated with that is going to be Planck's constant times the speed of light divided by 525 nanometers. So that's 4.14 times 10 to the 15th. Sorry about that. 4.14 times 10 to the, make sure I get it right. Yeah, negative 15th electron volts per second times 3 times 10 to the 8th meters per second divided by the wavelength, 525 times 10 to the negative 9th meters. That's the nano thing. And so we get our energy. So let's do that really quick. 4.14 times 10 to the negative 15th times 3 times 10 to the 8th divided by 525 times 10 to the negative 9th, giving me an energy of 2.36 electron volts. We'll say 2.4 electron volts. Okay, that's one of them. For the next one, it's everything is the exact same. 4.14 times 10 to the negative 15th electron volt seconds times 3 times 10 to the 8th meters per second divided by 525 times 10 to the negative 9th meters. When we calculate that, what we can do is hit second enter, and we can go back and change that wavelength. So instead of 525, so we're not doing 525 this time, sorry, we're doing 400, we're going to change that to 400. Change that to 400, and we end up with 3.1 electron volts. those are the energies that we're dealing with. So on the picture below, sketch the ground state and these two energy levels. So we're going to say these are both starting from the ground state. So the ground state is negative 5.6. Here's negative 5. Here's negative 5.5. So negative 5.6 somewhere along this line. So make sure that's just a line. Okay, so here's my ground state. Then we're going to add to that 2.4 electron volts. So 2.4 electron volts gives me the next one. So energy 1 is going to be the ground state, negative 5.6 electron volts plus 2.4 electron volts. Absorbing means we are gaining that energy. So my first state comes out to be negative 3.2 electron volts, which means we're going to have one that's right here. So when an electron here absorbs the 525 nanometer light, it jumps up to that level. For the second energy level, that's going to be negative 5.6 electron volts, our ground state, plus the energy from the 400 nanometer light. So that's 3.1 electron volts. Energy 2 comes out to be negative 2.5 electron volts. So that one is going to be here. So that's what happens when we are absorbed by when we absorb a 400 nanometer bit of light. Is everybody okay with that? Now, the next little bit says the white light is then turned off and it glows, and we produce one other wavelength other than the 525 and the 400. What could that be? Well, if we're looking at it, we've got our ground state down here at negative 5.6. So that's ground. Our n equals 1 level, so that's n equals 1, sorry. N equals 2 is the negative 3.2 electron volts, and n equals 3 is the negative 2.5 electron volts. So if the gas is cooling down, that means we could go from here to here, giving me the 525 nanometers. I could go from here to here. Oh, I did that backwards, sorry. That would be my 400 nanometers. This would be my 525 nanometers. And this would be a third wavelength of light. That one, the energy of the photon is equal to negative 2.5 electron volts minus negative 3.2 electron volts. That's my change in energy between levels. My change in energy, when we do that, comes out to be 0.7 electron volts. So the wavelength associated with that, lambda, is hc over my energy. So 4.14 times 10 to the negative 15th times 3 times 10 to the 8th divided by 0.7 electron volts. We can put that in our calculators on our own. That lambda comes out to be 1.771 times 10 to the 1.771 times 10 to the negative 6th meters, which is 1771 nanometers, if you wanted to do that. Okay, so we may not actually observe this, and this is a little bit of a tricky question. It may not be observed because that is very, very, very low energy. This is low energy light. That is outside of the visible range. visible range being from 400 nanometers to 700 nanometers. So this is beyond red light, which means if it's outside of the visible range, we may not be able to see it. We need a sensor that can get that kind of light. All right. Electron absorption and all that good stuff. Okay, so let's move on to some of the nuclear stuff. If you need a periodic table, you can find one on the interwebs. Series of tubes holding all of our stuff. So, nucleons, when we talk about nucleons, that's protons and neutrons. Those are made up of quarks. Those are tiny parts of fundamental particles. Don't really exist on their own. We don't isolate quarks. They have partial charge on them. Quarks are funny little things. Okay, so there are two common isotopes of oxygen. Isotopes. Isotopes, they're the same element, which means they have the same number of protons with different numbers of neutrons. That's all. That would be the difference. That gives them different masses and binding energies. That's all. It's a different isotope. Explain why the mass of the lithium-7 nucleus is less than the mass of 3 protons plus 4 neutrons. So lithium-7 is 4 neutrons and 3 protons. When we look at an element written out this way, that's the total number of nucleons, so protons plus neutrons. That is the number of protons. That's how we know it's 4 neutrons and 3 protons. Now, 4 neutrons and 3 protons together have a bigger mass than lithium-7. So inside of an atom, protons and neutrons have smaller mass than they do on their own. That mass defect is what we call that. Becomes binding energy. Now, we want the binding energy of lithium-7. So what we need for lithium-7, we need for lithium-7 is the mass defect. So my mass defect, delta M for lithium-7, is going to be 4 neutrons, so that's 4 times 1.007825 plus 3 protons, 1.007276 AMU, minus the mass of lithium, 7.0160045 AMU. So that gives me a mass defect of 0.03712.345 atomic mass units. Now, that doesn't tell me the energy. what we can do to find the energy, two different things. We can find the energy in electron volts. So our conversion here, and it's on our formula chart, is that 1 AMU is equal to 9.31 mega electron volts. This might be the easiest one to do. So the energy in electron volts would be the mass 0.0371234 times 9.31. So giving me the energy, that's just a simple multiplication of 34.56193 mega electron volts. That's one thing that we could do. The other way we could go with this is energy in joules. But to do that, we'd have to have, I'm going to do this in a different color just to make life easy. This change in mass is 0.0371234 AMU, but we'd have to multiply that by 1.66 times 10 to the negative 27th kilograms. And so that gives me a mass defect clear that out, 0.0371234 times 1.66 times 10 to the negative 27th. That gives me a change in mass of 5.939752. 5.939752 times 10 to the negative 27th kilograms. And to get the energy in joules, that's delta M times C squared. So we'd take that number and multiply it by 3 times 10 to the 8th quantity squared, giving me 5.34, apologies there, 5.346 times 10, it's a tiny number, to the negative 12th joules. When you convert between joules and mega electron volts, that happens to be the same number. They're just different approaches to getting there. Either way is fine. If I ask in electron volts, this is what you're going to do. Multiply it by 9.31. Okay. Lithium-7 could undergo alpha decay to form tritium. So, the complete reaction would be 7,3 lithium. So, an alpha particle is a helium nucleus, 4,3 helium. And if we, 4,2 helium, 3 is not helium, it's lithium. 4,2 helium, but we have to have the same number of particles, right? So if lithium is going to lose 2 protons, we're left with 1 proton, which means we have hydrogen. And if we have 7 nucleons total and we lose 4, we're left with 3. That's my complete reaction. In this complete reaction, total number of protons is the same. And the total number of nucleons, protons and neutrons, is the same. So these two things have got to add up to the reactants. These two things have got to add up to the reactants. Both of those things must stay true. In addition, charge has to stay the same. Calculate the mass change and explain why this process doesn't happen spontaneously. So, in this case, my mass change is going to be the the reactants. So mass of lithium, 7.0160455 minus the mass of an alpha particle, 4.002602 AMU, minus the mass of tritium, 3.0160492. That's going to give me my change in mass. My change in mass here comes out to be a negative number, negative 0.00264.665 AMU. In this case, we have lost mass. We end up with less mass than we started with. Is that right? Yeah. We end up with less mass than we started with. No, that means, sorry. That does not mean we lost mass. That means this is bigger than 7. We gained mass. We have gained mass. If my delta M is negative and not positive, I've gained mass. I have this much more mass in my products. This doesn't happen spontaneously because that means we would have had to gain energy spontaneously, and that doesn't happen. So in order for things to undergo nuclear decay, particles must lose mass. By losing mass, we have a spontaneous reaction. If we gain mass, that's a problem. We always want energy out of a spontaneous reaction. We always need energy out. Okay, xenon 135. So 135 tells me how many total nucleons we have, and we're talking about xenon. We look xenon up in a periodic table. We see that its atomic number is 54. And that's going to decay into cesium 135. And if we look up cesium, Cs, on our periodic table, it has 55. Cesium has 55 protons in it. So this is beta decay going on, right? And so what we have here is something that has sorry, not negative E, negative 1. What we have here is something coming out of this that is taking away a proton. What we have is a proton randomly turning in, we have a neutron randomly turning into a proton. So looking at our numbers, the total number of nucleons doesn't change, but I go from 54 to 55 protons. In order for that to work, I have to have gained a negative charge. The neutron loses an electron and becomes a proton. I wrote that backwards. Yeah. Neutron loses an electron and becomes a proton. There we go. That is your basic beta decay. It will be good for you to know beta decay and alpha decay. We've already talked about both of those. The third one, in what kind of decay does the identity of the parent nucleus not change? And it's gamma decay. In gamma decay, parent nucleus loses energy, but particles don't change. That energy is lost in the form of a photon. Sorry, I was going to say proton. That energy is lost as a photon. So in gamma decay, it's just a light decay. Energy comes out as light. And the mass decrease comes from energy leaving. So let's look at some decays, shall we? When bombarded with a neutron, so we're throwing a neutron at plutonium, it splits into strontium, something we don't know about, and 3 neutrons. So let's write out the equation. We're going to have a neutron. So the neutron has 1 nucleon with no protons, and we'll just call it a neutron. We're going to add that to our plutonium, 239. Plutonium is Pu, unfortunately. Second O. Pu. If we look at our periodic table, it gives me 94 protons there. The atomic number is 94, and it decays into strontium 88. And if we look up strontium on the periodic table, it has 38 protons plus 3 neutrons, 1 0 in, plus element X. Boom. We don't know what's going on with element X just yet. So that's the complete equation right now, but we don't know yet how many total nucleons we have or how many total protons we have. So if we look at the whole thing on this side for our product, we have 240 nucleons. Over here, reactants, I'm sorry, I did that backwards. On this side we have 240. On this side we have 88 plus 3 plus X. All that has to equal 240. So 240 minus 88 minus 3 gives me 149. That's the first thing. That's just from the total number of nucleons. Now we need to look at the protons, because we're not going to lose any protons here. So on this side I have 0 and 94, so 94 protons. And on this side I have 38 plus 0 plus X for the number of protons for X. So 94 minus 38 gives me 56. So this element X has 149 nucleons and 56 protons, which means its atomic number is 56. We go on our little periodic table, look it up, and it turns out that that is barium. 149 over 56 barium. And if we want to calculate the mass of this thing, and we'll do it in a couple of different ways. If we want to calculate the mass of this thing, it's going to be fun. We're going to do from our reaction, we have the mass of a neutron plus the mass of the plutonium is equal to the mass of strontium plus the 3 times the mass of a neutron plus the mass of barium. So the mass of barium is equal to the mass of the plutonium minus the mass of strontium minus the mass, 2 times the mass of a neutron. So we have numbers for all of that stuff. Okay, so 239, this is the mass of plutonium. 239.052163 atomic mass units minus the mass of strontium 88, 87.9056123 atomic mass units minus 2 times the mass of a neutron, which we have in our table. The mass of a neutron is 1.007825. Whew. So let's zoom out a little bit. So that makes the mass of our barium in atomic mass units 148.94258 atomic mass units. That's the mass of my species. There we go. That's all we're going to do. We're going to leave it like that. So how do we know the properties of the 3 kinds of radioactive decay? All right, so properties of 3 kinds of radioactive decay. We got an alpha particle. We have a beta particle. It's not a beta. We have a gamma particle. And so the properties that we're talking about are charge. Alpha particle is positive. It's just a helium nucleus, so it doesn't have any electrons on it. A beta particle is negative or positive, depending on what it does. And a gamma particle has no charge. By deflecting through a magnetic field, positive and negative particles turn different ways. And we'll draw that out here in a second. And different masses have different radiuses. And uncharged particles have no deflection. So I'm gonna move over a little bit. So if we have a magnetic field that's directed into the page, this is good for a little bit of review. And we send an alpha, and we send an alpha particle, which is positive, into that magnetic field. The velocity is up, magnetic field is into the page, and so that positive particle would turn this way. If we sent a negative particle, it would turn in the opposite direction, and a gamma particle, which doesn't have any charge, would go straight through. So we can determine the charge based on which way it turns in the field, and if it had less mass, it would turn tighter. So if we knew the velocity and then we saw which way it turned, we could determine the charge, and how much it turned, we could determine the mass. So all of this is what we see in a magnetic field. The thing that we called this mass spectrometer. We did that in our magnetism unit. Okay. What quantities must be conserved during a nuclear decay? So, in this case, charge is always conserved. Number of nucleons. That top number. I'm not going to say number of protons, although that's true because you can have negative with a negative sign. But we get that with charge. That's what the bottom number is going to tell us. Number of nucleons and momentum. Because guess what? It's always conserved. to that, mass plus energy is also always conserved because of the E equals mc squared thing. So we might lose some mass in this reaction, but it's becoming energy. We might lose some energy here because it's becoming mass. All right. A hypothetical particle and its antiparticle collide in space and annihilate each other, creating 2 photons. Each photon has this much energy. So why must there be 2 photons created instead of just 1? The answer there if just 1 photon left, so if we had a little photon going this way, the total momentum of the system would have to be this way. That's not the case. The 2 photons are going to have to be going in 2 opposite directions, so the total momentum remains what it was before. So the 2 photons must move in opposite directions. Because of that conservation of momentum thing. Calculate the mass of the particle and antiparticle. All right. So we have 2 photons. So the energy total afterwards is 4 mega electron volts. So the particles that did that, mc squared total, delta mc squared, has to equal 4 mega electron volts. But there are 2 particles, right? So twice the mass times c squared is 4 mega electron volts. If they're identical, they have the same mass. Well, if they're identical except for their charge, they have the same mass. So the mass is 2 mega electron volts divided by c squared. So there are 2 ways we could go with this, just to reiterate a point. If we want to stay inside of AMUs, the mass is equal to two mega electron volts, and then we have a conversion here of so divided by 9.31 mega electron volts over c squared per AMU. Tell you what, it's a conversion, right? So 9.31 mega electron volts c squared, 1 AMU. That gives me 2 mega electron volts divided by 9.31 mega electron volts per c squared gives me 2.148228 times 10 to the negative third AMU. That's with using the AMU conversion. The other way we could do that is by converting the 2 mega electron volts into joules. So that's 2 times 10 to the 6th electron volts times 1 electron volt and 1.6 times 10 to the negative 19th joules per electron volt. So that gives me an energy, and we'll do the calculator for this, 2 times 10 to the, I'll turn it on, 2 times 10 to the 6th electron volts times 1.6 times 10 to the negative 19th joules per electron volt, 3.2 times 10 to the negative 13th joules. And if I want the mass from that, this is going to be my mass in kilograms now, because we're in joules. It's going to be energy, 3.2 times 10 to the negative 13th joules divided by c squared, 3 times 10 to the 8th meters per second squared. And it gives me my mass in kilograms. Wrong thing. So take that and divide it by 3 times 10 to the 8th squared. We get 3.55 times 10 to the negative 30th kilograms. Now, if we want to compare those things, here's the deal. Compare that on your own. Energy in electron volts, we're going to use this 9.31 thing. Energy in joules, we're going to go through all of this. It's up to you. Okay? That's our review. Good luck studying for your test.